Assalamu alaikum. It's day 10 on 13 summer school at LHC Physics. Today is very good morning. You can see greenery all around. So this is basically MOQ, the hostel for boys and girls, and this is BOQ, and this is actually the cafeteria. Okay, and this is the technical block where mostly silicon detectors are made by NCP and which were used in CMS on LHC. And this is basically the main auditorium where the lectures held by the foreigners and by the local professors. And this is all the way NCP, and it's day 10, and we have a workshop visit of total 11 days. So today is the second last day at NCP.
Spontaneous symmetry breaking, when the local symmetry is broken spontaneously, is precisely equal to the number of generators for which this condition is satisfied. And that's exactly the same condition which we have in the Goldstone theorem. So that's why the number of Goldstone bosons is equal to the number of the gauge bosons which become massive. Okay, so let's now finally talk about, please. I'll stay at the massive.
Okay, but it seems to me now that's twice the same condition, so I'm a little confused. So the Higgs bosons are the massive ones, right?
No, and his boson is not the Goldstone boson.
The Goldstone is this one, no?
Yeah, the Goldstone is this one.
The
Higgs is this one. Yeah.
Then we have the gauge boson. And they combine with the Goldstone boson at the end.
Yeah, that's one way of saying it. That's one way of saying it. You can say that the gauge bosons, they eat up the Goldstone bosons and they become massive. So that's why exactly the number of gauge bosons which become massive, that's precisely equal to the number of the Goldstone bosons. Okay, so how much time is left? 5 minutes?
Yes.
Okay, so let me finish it in 5 minutes. So before I go to the last topic, which is the recipe of building the Lagrangian, I just have to talk about the chiral fields as well. So starting from a Dirac field, we can split into the two parts. You see the sum of these two parts is the original Dirac field itself. And this part over here, that is called the right chiral field. And this part over here, that is called left chiral field. So precisely speaking, these are the definition of left and right chiral field. So the Dirac field can be split into the right and left chiral field. And similarly, the corresponding bar field, that is split in this way. And why we call them the chiral field? You see that this operator, gamma 5, which is the gamma 5 matrix, I call it chiral operator, it turns out that psi right chiral field and left chiral field, these are the eigenstates of this chiral operator. The corresponding eigenvalue is +1 and -1. So that's why we call them the chiral field. So let's see that what happens to the Lagrangian if we split the Dirac field into the chiral fields. So we have two types of terms in this field, in this Lagrangian, kinetic energy term and the mass term. So if I split the kinetic energy terms into the chiral field, then you will get the four terms, and you can show with simple exercise the contribution of these terms is zero. It's not cancelled actually, the contribution of every term is zero. So we are left only with this term. So this is called a current, and we call it a vector current because it's vector in nature. And this showed that the vector current, when it is separated into the chiral field, then the right coupled with the right and left coupled with the left. But it doesn't happen in the mass term. So if you separate the mass term into the chiral field, then once again you will be getting the four terms. But in this case, the contribution of these two terms will be zero. So left will be coupling with the right, and right will be coupling with the left. So this is how this Lagrangian split. This is how the kinetic energy split, and this is how the mass term split. Okay. So the interesting thing which we notice over here, let's suppose that the mass is zero. Okay, so then your Lagrangian is this one. But you can also just construct it from the right chiral field as well as the left chiral field as well. You don't need both right and left chiral field if their masses are zero. We need both of them if the mass is not equal to zero, because mass term couples them. But if the mass is zero, you can construct the Lagrangian only from either right chiral field or left chiral field. But the most important thing which we have to carry from this slide is the following. You see that sometimes we impose an internal symmetry which is called chiral symmetry. So what happens in the chiral symmetry? In chiral symmetry, the symmetry is defined in such a way that the right-handed field and the left-handed field, they transform in a different way. I got no
I've also been surprised to be here because I don't have the first idea about particle physics. So my ideas of a collider is protons go boom boom, which is not a very sophisticated theory, I admit. So I know a little bit about machine learning, so I thought I'd share sort of an opinionated overview with you. And so before I start, I should start with a little bit of a disclaimer. Machine learning these days became a huge and very, very varied and complex field. So we have now to the tune of 30,000 preprints appearing each year. So it has, with the growth, for some reason, resembles Moore's law, which I'm not sure I appreciate. So there is a course that I think Rashid very kindly shared with you. It's composing 50 hours, composing the very bare minimum. So when Rashid told me, could you do a machine learning intro? And by the way, you should condense this into 3 times 45 minutes. I was a bit, it's a challenge to say the least, but I'm happy to take on that challenge. Right. So I thought a little bit about how to go about this. So whenever we have these huge and complex fields, there are a couple of ways to approach it. So I thought let's take a book, let's take a page from the medicine playbook and sort of divide it in 2 parts. And the first part, and that's the part I'm going to be focused on today, is sort of a high-level overview. So when we look at some complex systems, and we look, for instance, at the human body, which is very complicated, or the human brain, which is still very complicated, we could start with a high-level overview. And so, sort of, from one perspective, we could start with an anatomy. Which parts do we have in our brains or in our body? What parts make up that machine learning. So that would be an anatomy of machine learning. And then maybe a physiology of machine learning. That would be how, in principle, those parts work together. And I'm going to try to explain how and why machine learning works. And then I'm going to talk about something called regularization. And then we're going to briefly touch on applications. And I'll give you an overview. It's not going to be focused so much on high energy physics. I'm going to talk about applications in solid state physics, but the point I want to make there is not so much which specific applications we are doing, but more what are the sort of lessons, what are the common threads that run through all these applications. All right, so that's part one. That's going to be these 45 to 50 minutes. In a second part, I want to do one thing in detail. And so I want to give you some tool that you can readily apply to whatever problem you have. And I want to walk you through it in very much detail so you understand every part of it. And that's going to be a thing I'm going to focus on is what's called the singular value decomposition, which is a crucial tool, and its generalization, which is a crucial tool in machine learning, the basic tool in machine learning. And I think it pays off to understand a little bit about it, to make sure that, and then to be able to apply it. So that's going to comprise the second and third part of the lecture, which we're going to do tomorrow. All right, with that out of the way, I'm the kind of speaker who loves to get questions. So whenever you have a question, don't be shy to ask it. Since it's unlikely that you're going to have to already have a question at this point of the lecture, I'm going to flip the playbook and ask a question of you. So you came with this with some idea, preconceptions. So I'm going to ask the question, what is machine learning? Any ideas, any definitions? If somebody would ask you, now what is machine learning? You have heard a little bit of that. What comes to mind?
It's an experimental observation. It's not some abstract, theoretically motivated idea. And as I show you, there's quite a bit of evidence in favor of dark matter. And we have no idea what it is. I'll discuss a couple of the leading ideas. One is massive neutral particles that we might be able to make at the LHC, which I've already mentioned in previous lectures. And the other possibility is that dark matter is formed of sort of waves or clouds of ultralight ozonic fields. And I'll discuss that in the latter part of my lecture. And that will actually lead me on naturally to discuss also the search for gravitational waves, which I'll spend a few minutes discussing at the end of the talk. Okay, so the story of dark matter, as we currently think about it, originated with Fritz Zwicky, who you see here, a Swiss astrophysicist working in the US, who made observations of the Coma cluster of galaxies. And what he observed was that the galaxies in this cluster were moving around too quickly in the sense that in order to hold those galaxies together, you needed a stronger gravitational field than what was provided by the visible matter, in particular the matter in the galaxies themselves. So he said that in addition to the gravitational field that we can calculate, there must be some additional gravitational field generated by invisible matter, so-called dark matter. So as I said, that was in the 1930s. I think it's fair to say that his proposal did not find general acceptance until the 1970s. And what convinced astrophysicists that this idea of dark matter should be taken seriously was the observations by the astronomer Vera Rubin, who you see here, who measured the velocities of stars and dust orbiting individual galaxies. So, in the same way as Fitzwickley found the clusters of galaxies, she found that inside the galaxies, the motions of the stars also required strong that provided by the visible matter. So this provided rather strong evidence for dark matter, and I think it got astrophysicists, as I said, taking the idea of dark matter very seriously. Starting in the 1970s, subsequently, a lot more evidence for dark matter has come in. I'm not going to go through all of it. Dark matter is believed to play a key role in structure formation, which I'll discuss a little bit later on. And perhaps the strongest evidence for it, and most precise measurement of the dark matter density, comes from observations of the cosmic background radiation, which I'll discuss in a moment. Let's do the universe. The cold dark matter makes up a larger percentage, somewhere between 25 and 30%. So much more than the regular matter. Other things like microwave background itself and neutrinos make up a much smaller percentage. Most of the density of the universe is in fact in something that we call dark energy, which was a possibility voiced out by Einstein back in the 1910s. It's what he called the cosmological constant. So the division of matter in the universe looks quite strange, but there's many convergent indicators that confirm these calculations are based on cosmic microwave background. So, what might this dark matter be? Well, we actually have very little information. We know that it should not have electric charge, at least not very much electric charge. If it had electric charge, then it would emit electromagnetic radiation. So you can avoid that argument by postulating that dark matter particles have, let's say, 1,000th of the charge of the electron. But I don't find that idea particularly appealing. For experimental evidence for some physics beyond the standard model. But you might say, just a moment, in the standard model we have neutrinos. Could they be dark matter? So, they certainly have certain advantages. So first of all, we know that neutrinos exist. Secondly, we know that neutrinos only have very weak interactions. Also, from observations of neutrino oscillations, we know that they have small masses. The trouble is that those masses are very small, less than an electron volt. And as such, they're not able to form the large structures that we see in the universe. Or more accurately said, that they run away from the smaller classes of structures, like satellite galaxies. But neutrinos alone could not grow all the visible structures in the universe. And in 1916, although we tried to retract the prediction in 1936, but the referee of this paper convinced him that actually he was right the first time. So a gravitational wave would have a similar effect to an atom interferometer to what it has on a laser interferometer. It would induce a phase shift with a characteristic frequency which depends on the frequency or wavelength of the gravitational wave source. Okay, so where could atom interferometers fit into the landscape of gravitational wave detectors? So as you know, the original discovery of gravitational waves came from the LIGO and Virgo experiment. Here I illustrate the layouts of the LIGO atom interferometers.
Shaking underneath, trying to take me alive. Get ready for the fallout. Can't stop me now. I got no rival. I'ma find my way through the blood and pain game of survival. Any time or place, watch 'em run away. I got none. I'll be standing on my own, never gonna take my throne. I got no rival, watch 'em run away. I got no, I got no rival. Tell me now, what you gon' do? We can do this face to face. The reckoning is coming real soon. Doesn't matter what you say. Try to tell you this is my moment. Can't take mine 'cause I own it. Don't you know